very beautiful topic about fascia. As we look at this fibrous component, fascia connects the body from the skin all the way to the bone level. And this schematic is exactly to demonstrate the continuity of the fascia through its collagen fiber network, starting at the skin. You can see on this diagram or this image, this is not just a drawing. These are actually images that I took in the laboratory in the dissection lab working with fresh tissue on human cadavers. So the dermis you can see is a epidermis is what we see on the surface. Epidermis is made out of epithelial cells, and there's not really a collagen structure to it, but very, very close to the surface. When you go down to the dermal level, you hit a lot of collagen, which I'm going to show you a couple more images of that from the deep surface in a moment. But following from the dermis, you can see how there's these white fibers that root down into the adipose layer, and they root almost like roots of a tree. They have that same kind of stability that they create for this very important layer that regulates our thermal regulation. It has to do with hormone. It acts as a gland. It has functions for our insulation as well as for nerves to travel along. So where do the nerves go through the fat? Well, they have to have a wall. So do the vessels that go to the skin surface. And those collagen walls that you see are septa. So they're called the retinacula cutis. The retinacula cutis create a honeycomb type structure for the fat lobules to be organized and to have a stable place to live. Going deep to that surface of the superficial adipose tissue, there's another layer that I re-emphasize by drawing a line. We call that the superficial fascia membrane proper. And this really is a division of the fat. Above or superficial, you have the superficial adipose tissue. This is so strongly anchored to the skin. Below it, you have another layer of adipose tissue, but it has more flexibility, it has more glide, it moves in relationship to the muscles. That adaptability to the muscles movement is so important, as opposed to the connection from the membrane to the skin, where there needs to be more of an anchoring and stabilizing as we reach out into the exteroception to the surface, the world that's outside of our body. Below the deep adipose tissue layer, what you see is a totally different organization of the fibers. These are collagen fibers that are lined up next to each other in a very tight and organized fashion. They are all going in the same direction, and you can see it as that silvery white layer of the deep fascia. Deep fascia is organized like an entire sleeve or stocking on the limbs. On the trunk, its organization is slightly different, where the most stable parts of that aponeurotic deep fascia we find in the back as the thoracolumbar fascia, and in the abdomen or the front of the torso as the abdominal the rectus sheath. And then each muscle has its own fascia, and you can see that as a kind of a lighter, more gauzy looking fiber organization of the epimysium of each one of the muscles. Then we go down into the muscles, and even the muscle fascicles and the muscle fibrils, they are also organized by fascia. This time it's collagen type 3, which has a more adaptability to it to allow for the gliding and sliding as the actin and myosin do their contractile work. Not on this image. If we continued to go, we would then hit the bone. But before bone, we would come to periosteum, which is also a part of this collagen network. So you can see that starting at the skin surface all the way down to the depths, there is a change in organization to the fibers that are mostly collagen type 1, also collagen type 3, with quite a bit of elastin depending on which layer that it's in to give it a more flexible orientation. Okay, so let's take a look at these layers separated out. These are images that a lot of my students have never really seen. Our anatomy books tend to jump straight to the muscle, and they skip these other layers because it doesn't show the individual structures that we're used to talking about, the ones that do contractile force. But before you ever get to muscle, first you have the deep surface of the skin, part of the collagen network that connects the skin to the muscle. It has to start at the surface. And then you can see where the skin has been reflected, and we are at that adipose level, that where there's that honeycomb structure full of blood vessels and nerves as they travel through that network. And then that beautiful silvery white deep fascia of the thigh, you can see here. This is called in this region the fascia lata, which is fully enveloping the thigh, also creating septa that go to the bone that anchor the outer layer to the bone, but also grouping the muscles into compartments, and then the muscle that we recognize. If we look at these ish now close up, so this is taken with also just a camera and they're not zoomed in very much. This is pretty much just holding the camera quite close to the tissue. You can see the back surface of the skin, that deep surface of the skin. The organization of the fibers is one that promotes adaptability. Our skin has to be able to move and adapt to muscle contraction, changing of shape as we stretch and move through life. Then if you see the adipose layer, we've separated the adipose slightly so you can really see the white fibers as they group the adipose into lobules, these bundles of fat cells that gives this more adaptable, soft layer that we come to before we ever get to the deep fascia. This is everywhere on the body. No, regardless of the size of the person, there's always an adipose layer before we come to the deep fascia. The deep fascia you'll see in this image is so different. The way the fibers are very structured, very organized, and all going in the same direction. This organization of collagen allows fascia to be incredibly adept to force transmission, which is needed from where this fascia is from. I think maybe there's a mute that can be for one of the viewers. If you can mute your microphone, that would be great. Thank you. And then below the deep fascia, we come to the muscle. And you can see it's very different in the muscle. You almost can't see the fascia, but you can see the results of it being there as it's grouping the muscle into bundles that gives that very familiar grain or texture to muscles that is organized specific to its function. This close-up picture is of the low back. This is the thoracolumbar fascia. You'll notice immediately that the fibers are going in more than one direction, and that's because the thoracolumbar fascia is where many muscles come together, and you can see exactly where the muscle force is transmitting because the collagen has become organized in that area in the same direction of force. Collagen is non-contractile. The muscle contracts and then it tractions into the collagen network. And those collagen fibers are aligned perfectly with absorbing the force or permitting force to transmit to the bone to create movement. So you can see the overlapping fiber directions, one going from the bottom corner to the right and the other one coming opposite to the left. You'll find this in many areas of the body where there's multiple lines of movement. We've come around to the other side of the body with this image, and you can see this is similar fibers going in different directions with some adipose lobules still remaining on the left side of the screen. This is from the rectus sheath. And in the rectus sheath, you have the external obliques, as well as the pectoralis major that's coming up and down and crisscrossing with these collagen reinforcements. Zooming in with about 40 times magnification, we can get another view of seeing how the organization of the layers of the fibers permitting force, these fibers are part of our body as we're developing, but they become based on how we use our bodies. So not everyone looks exactly the same. And even in the cadaver lab, we can see that. Some people have created a lot of reinforcement in parts of their body that they use often. So if they were someone who was athletic and was jumping a lot, or perhaps someone that didn't move as much and they became stiffer, didn't use their muscles as much, their fascia sometimes will become very dominant, especially as we age. So we talked about fiber organization. There's still fibers in this. This is also a part of the fascial system, even though it looks completely different. In this image, what you're seeing is loose connective tissue. And loose connective tissue shows up wherever glide is needed. It helps things to move and without friction. You'll see a lot of water in this. There's also a lot of hyaluronan, which is the most common glycosaminoglycan that you'll find in fascia. The fiber organization here reorganizes, keeps connection, but with a great deal of freedom of movement. So not just fiber, but also fluids are what make our fascial system what it is. In this image, we can see the relationships of these organizational layers of fascia and how they connect to each other. Once again, how I was describing earlier that strong connection that exists from the dermis to the superficial fascia, you can really see that as we've actually cut away part of the dermis, but left it connected. As a traction and pull on the fascia, you can see how this skin, the dermis, is rooted strongly into the adipose. There's no gliding relationship there. It's one of stability. It's one of strength. Then we go below the adipose tissue, in this case on the abdomen in the center image, and you can see how this is a different kind of relationship. Not so strong, not so rigid. It has a lot easier to separate, a lot easier to move and adapt. This makes sense because when you're moving, a lot of movement occurs throughout the center of the body, and the body has to have that adaptation so that you don't become stiff or stuck. On the picture on the far right, we see deep fascia's relationship with muscle. This is the same fascia that you saw in the previous image, but in this case, we have a light behind it. And you can see it's a very thin fabric, but incredibly strong. That's because of the fiber organization. Its relationship to the muscle is also very loose. It's one of glide. So the muscles can freely glide beneath the deep fascia without interruption or hindrance. Another image here to show as you're stretching the fibers, you can see both fibers and fluids. This is once again on the abdomen, showing the superficial fascia and the loose connective tissue that connects it to the abdominal wall and the muscles. Zooming in a little closer, we can see both in the adipose layer as well as in the relationship of the adipose to the deep tissue, or I believe the deep fascia. You can see the fibers are still present, but with so much water and hyaluronan, it gives it a completely different quality, allowing things to move. So the point to be made of this is that all fascia is made of the same three primary ingredients. You have the gels, and the gels are water-based, and their primary macromolecule is the hyaluronan. The glycosaminoglycan we find the most of is hyaluronan. It also has a fiber component. These fibers, under a microscope, you can see so easily these organized stripes. The fibers component consists of protein fibers, primarily collagen type 1, which is the very strong force transmitting kind of collagen. Collagen type 3 has more of a web-like organization, is more adaptable, as well as elastin, which gives even more stretch and adaptability to the tissues that need it. And then the cells. And the cells are very sparse in the fascia compared to other parts of the body. Really, it's defined by its non-cellular components of the gels and the fibers, or the fluids and the fibers. But there still is a cellular component which actually creates both the gels and the fibers. The cells that create the fibers are the fibroblasts. The cells that create the gels are the fasciocytes. But you will also find in fascia, as we've already seen, adipocytes, as well as a high level of our immune cells that travel through this system. The fascial system as a system connecting all of the collagenous tissues, which is a new definition that was developed to help express the continuity, the continuance, not seeing fascia as separate things, but as a unified, holistic view of this network, includes all of these different fascial-based structures. And based on their organization of the cells, gels, and fibers, you come up with this many variations of how the tissue can appear, as well as what facilitates its function. This is a quote that I wrote for a friend in her book, and it just really summarizes what we're talking about today, that we are woven from these beautiful collagen silvery threads and glistening dewdrops from skin to bone and head to toe. Every part finds its whole through our fascia. Back to you, David.
Thank you, Rochelle. And here we are back now in fluid land, as Rochelle has mentioned, and I will elaborate on. Fascia is rich in fluid, specifically hyaluronin, which you often see in products as hyaluronic acid. The fascia biosynthesizes the hyaluronic acid via cells called fasciocytes, those darker blue dots you see in the bottom picture. And they're predominant in the sliding zone between the muscles. So what happens is the muscles slide back and forth on each other, and as they glide, that shearing motion stimulates the fasciocytes mechanically to produce more hyaluronic acid so that the muscles keep sliding and gliding. Now, when they're not getting sufficient stimulation through movement like Tai Chi, or really any movement, that hyaluronin gets thick and sticky because it's not getting that constant mechanical stimulation. And that can cause problems in the body because then things suddenly don't slide and glide so well. So another muscle or myofascial unit, I think is a better way to think about it, happens, and compensations develop. Yes, there's someone speaking. If you could mute your microphone, I'd appreciate that.
We can.
Oh, maybe we can do, I have to escape.
Yeah.
Where do I do it?
Here.
Oh, there.
Perfect.
Okay, no problem. Thank you. And now back to the show.
Just if you want.
hmm I, I'm enlarged enough already, Rochelle. Don't need more of that. Okay, we back to the screen. There we are. Whoops. I did it in reverse. All right, you'd think this was my first rodeo. All right, we good to go here. So, lack of stimulation leads to densification. Okay. Now, this brings us to another aspect of the fluid system in the fascia, because often the language that we use, how we choose to look at things, can shape our experience of what we see and how we think about it. So remember those pictures I showed you of where I live and Rochelle lived, and I said, keep those in mind. Bring those back to mind. So in 2018, this bombshell dropped in the science world about the interstitium. And you see the name of the paper there, structure and distribution of an unrecognized interstitium in in-betweenness in human tissues. Now, in the media in my country, in the US, this became science finds new organ. Now, nowhere in any of the literature did it say science found a new organ. That is not there. It talked about this interstitium, this different pathway through the body, right? This is again a typical slide of what you would see in the organs, the peritoneum there being pulled back, and what you're seeing are layers of epithelial tissue and what is thought to be hard collagen barriers from one aspect of the organ to another aspect of the organ. Thick, densely woven collagen. That's how it goes. That's how the body is. We've known that for 100 and some years, longer than that probably, or did we? So here you're seeing a typical biopsy slide. And what they do when they make a biopsy is they take a cross section and then they have to take the fluid out and dehydrate it. And they have to put it through like a 6-stage process to create the biopsy that they then send to the biopsy lab to analyze and tell you if there's a problem. And it creates these artifacts. So if you look at the blue at the top there, you can see this white space. And if you look at the bottom with the more magenta color, you can also see at the top a magenta, a darker purple, and then there's some white stuff and then more magenta. That white stuff are tears in the collagen. That's an artifact of the process of cutting it and making a biopsy. But then one day, somebody used a confocal laser endomicroscopy. So this is a way of analyzing tissue by swallowing a dye that lights up the tissue, and then you put a sensor on it, a confocal laser microscope to be precise, and you get an image like this. Now you can see it's got what they call a reticular pattern. That's science for net-like. And it baffled the researchers. They didn't understand what they were looking at it from the top down as opposed to the side. So let me compare those for you. So here you go. So on the left, you can see quite clearly that that is a cross section of this tissue. And on the right, this dye is showing that same area of tissue from the top down. So they went to a friend of mine, Dr. Neil Thies, who was a liver pathologist, and they said, "What do you think this is?" He didn't know. And he just went through a lot of different books trying to find in all of his pictures of biopsies a biopsy that looked like the one that you see on the right side of the screen. Couldn't find one. So he had to figure out, how can we create a picture that looks like the one on the left using what you did on the right? Then I can see it from two different angles. Maybe we can figure this out. And they did. And this is what they got. So again, on your right, typical biopsies, you can see the tears in the collagen from the process. And on the right, you're looking at a dye, and you're looking at the top down, no tears. It's a fluid-filled space. And what was thought about for decades in medicine was that these tear artifacts in the biopsies was where the collagen was torn. It's not. It's a fluid-filled space. And they found it everywhere they looked. The bladder, the pancreas, the esophagus, the lung, the stomach, the colon, the fascia itself. This fluid-filled space, this interstitium, ran everywhere through the body, and it was bordered by collagen. So this model is wrong. It's just wrong. It was good. It was a good guess 100 years ago, 150 years ago, but we now know that's wrong. So what does that mean? So here's a diagram, and what you can see here is the interstitial fluid, the interstitium itself, full of gels, as Rochelle talked about. And then there are these matrix bundles of collagen and also cells. But the focus on this chart is the fluid. I don't think it's very dissimilar from a typical slide from Gray's Anatomy, where you can see those branch-like fibers of collagen and the cells and the elastins and the macrophages and things. Uh, Here's a picture of just the collagen and elastin fibers in the fibroblasts, the cells that build the collagen. Here is a picture from the work of Carla Stecco and her fascial anatomy atlas for the human body. And you see it looks very similar to the pictures you just saw of the interstitium. And the diagram is not dissimilar. And you can see the layers that Rochelle was showing you earlier in this diagrammed form. And then there's the work of a French surgeon who used an endoscopic camera to do a 50 times magnification in living human bodies and his view of the fibers when he put it in there. And then from Chinese medicine, there's the triple warmer meridian. What if we're all looking at the same thing, but because of language, because of concepts, because of preconceived ideas, biases, some of them may be accurate, some of them not, we're all seeing the same thing a little bit differently, but it's all pointing in the same direction. It's fiber and it's fluid. Where you choose to look, how you choose to look might make a difference in what you think you're seeing. Are you looking at the land and the mountains and the topography, or are you looking at the water that runs through the land and the mountains? When really, they're all part of the same thing. And that takes us to, so what is this fascia stuff? What does it do? Well, another researcher that I know calls fascia your soft skeleton. So, we always see the bones and the skeletons, models and such, but it's the fascia that's holding it together. But you never see a skeleton model that's held together that way. It's held together by screws and plates and hinges and things that we don't have in our bodies. So your bones are your hard skeleton. Your fascia is your soft skeleton. I often tell my patients that, and they kind of go, "Oh, I get that now. Thank you. Cool." But when you look at the body this way, it brings us to a different model for biomechanics, that we are not a series of levers and pulleys and hinges and doorknobs. We are what's known as a tensegrity structure. So there's me in Washington, D.C., standing under the Needle Tower, which I want to say is 60 meters tall. It's big, it's tall. It is freestanding on the ground. It anchors itself into the ground. There's nothing holding it there. And if you look at the picture on the right, you can see how those stainless steel tubes are suspended in this contiguous wire. So think of those stainless steel rods as the bones and the wire framework around it as the fascia. And you've got the idea. That's tensegrity. Now, this idea can build large structures that are incredibly stable and incredibly resilient, like geodesic domes. And here is a little bit of tensegrity in action. I found this Tinker toy when I was in Amsterdam. So you see, when I pull on it, I can't pull on one area without it shaping and changing and distorting other parts of the same structure. And I submit to you that we are tensegrity structures, tension and integrity. And when you put bio in front of it, that takes this architectural idea of tensegrity and moves it into the biological world. So it is tensegrity, but biotensegrity refers to it specifically in organisms as opposed to architecture. Okay. Now, we are tensegrity structures, fascia responses, supply and demand. The things we do repetitively over and over and over again can distort and change the tensegrity of the body, our natural balance between the river and the land, between the fluid and the fiber. And the body is adaptable enough to reset itself. But if we do the same thing over and over and over again, and if you were here with me in person, I would be jumping up and down on one leg. And I would say, see, if I did this for 4 hours a day, after about a month, my entire collagen network would start to reorganize itself. And by 3 months, I would have a very weird and different body because I spend 4 hours a day hopping on one leg just to prove a point. I would never do that, of course. But that's how the body remodels itself from this mechanical message of pressure that signals the cell called the fibroblast to decide where I want more collagen to support my daily habits. This is why being active, being athletic, also doing things slow, focus things like Tai Chi, like yoga, like Qigong can make a difference in how your body shapes and reshapes itself. And you can get a reset. So if I'm that poor fellow on the right, and that's why I sit in front of a computer 8 hours a day, I'm going to look like that when I'm not in front of my computer 6, 9 months from now. So we're adaptable, but we can also maladapt. So this is an example from the anatomy trains model of the lateral line, which is a force transmission system from the side of the foot all the way up to the side of the head. Now, what I want you to do at home, and I don't know how the camera's going to pick this up, so I'm just going to do my best here and hopefully not kill something on the chair. There's a cord there. Okay, thank you. So what I want to suggest that you do is I want you to stand up and I just want you to raise one arm or another arm. I'm going to tilt this up so hopefully you can see most of me, whether you want to or not. And I just want you to take your arm up and just do a simple side bend at the waist. You're just going from right to left. Okay? Not terribly exciting. Now, if you take your feet a little wider, so your feet are wider than your hips, and you take your right arm up again and stretch, 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 reach, reach, reach as far as you can to the ceiling, and then bend. You're going to have a very different experience of that stretch because it's that activated tension that takes the fibers of the collagen and allows the body to have a different experience, a less mechanical experience, a more organic experience of that stretch. So stretching with intent and directed traction or tension actually activates more of the collagen matrix and less of just the muscles and the bones and the hinges, if you will. I'm going to skip over the next couple of slides because I thought we were going to have a live studio audience and we were going to do a really cool experiment in tensegrity with the human body. But we're just going to have to skip that. Now, this is the anatomy trains model, which I understand is quite popular in China. I'm going to flex here. And if you look at that picture, that's me on that ladder holding a camera. And that's Tom Myers down on the floor after we spent a week dissecting out all these things, like the superficial back arm line that you see there at the bottom of your screen, which will complete, because everybody knows the trapezius, right? The shoulder muscle ends at the spine. Well, it doesn't, because we were using fascia sparing dissections and we went right over the spine into the other trapezius. It just happened as we were doing it. There was no hard end from the trapezius into the spinous process on the bone. So you could think about the trapezius as two muscles on each side or one interconnected muscle in the horizontal aspect. If you turned that specimen over, which we did but did not photograph, we actually saw horizontal fibers running from one side to the other. And there's a close-up of what I just talked about. I was going to do an experiment in tensegrity here utilizing this picture, the deep front line. I took that picture with an iPhone 4. That's how old I am. And sometimes I see it online and I think like, oh, why did I do this? Because I see a lot of people take this picture out of context, and I'm trying to put a stop to that. But what this shows is a continuous fascial meridian, if you will, from the deepest muscles of the foot and the inside of the calf up the adductors of the legs through the psoas into the diaphragm, around the pericardium of the heart, and the pleura of the lungs, up the esophagus into the tongue. Now, if you have flat feet, pulling on your tongue is not going to give you arches, okay? So if you hear that, just go like, okay, I'll see you later, okay? But this can be a continuous tensional network. And I've done an experiment, it's in my book, where you can you can try to pull somebody over, but then you can have them jam their tongue up into the roof of their mouth, and suddenly it's harder to pull them because it's activated the tension in this line and made them more stable. And I'm beginning to understand that there is a concept of that tongue to the mouth in some martial arts. And I was hoping to get into a discussion about that here this weekend. Hasn't happened yet, but I'm hoping it will. So I was hoping you were going to get your mind blown when you tried to do the experiment and saw it happen in front of you. But I'd like to say he's my friend, but I don't know him, but I love him. Neil deGrasse Tyson. I always believe I love science in general, not just fascia science. And I love his idea that every day you should have your mind blown at least once. That's living in my book. But here's the thing. Tensegrity isn't just fascia and muscle and bone. Tensegrity is cell deep. So cells have the ability to detect what's going on in their immediate environment. They can feel the stress and the tension in the body. They do it through a very specific receptor called an integrin that sticks out beyond the cell wall. Now, there's lots of different cell receptors in the cell wall, and some take in chemical messages like, ooh, that's some caffeine, and I got a lot to talk about, so I better get some of that caffeine into my cells, give myself some more energy. But the integrins respond to tension. So here's a diagram from my book of mechanotransduction. What you're seeing here on the left, where that arrow is pointing, is individual collagen fibers. And the collagen fibers in your collagen matrix, your fascia, connects to the integrins of every cell in your body. There's over 30 trillion of those. Think about that connectivity. And when that collagen gets pulled, those integrins send a message into the nucleus of the cell that changes, can change how the DNA in the nucleus of the cell respond. So this has the potential to create changes on the cellular level. This is something we are still learning about. How can we take this principle to get better clinical outcomes? But I would submit to you, every one of you who's listening now, who works with acupuncture, you're doing this whether you know it or not. You're engaging in this mechanotransduction process. This has something to do with the systemic changes that you see in your clients and in your patients. Now, this is Don Ingber, who is one of my heroes. Um, he was the one who figured out that the structure of cells is a tensegrity structure, and that if you manipulate the cell, it changes the function of the cell. So mechanically restructuring the cytoskeleton of the cell, the network, tensional network inside the cell, can change the function of the cell. Now, he did experiments with this. He found out a lot of things, but the takeaway, your takeaway from this, is when cells were allowed to round, they tended to go into apoptosis, which is cellular death. But when they were stretched, they were alive and they thrived. The cells proliferated. Okay? Kids know this. Movement is just magic, right? When we get older, we stop moving. We need to not do that. We need to just move more well throughout our whole lives. And this is one of my favorite things from Don. I'm just going to read it: from the molecules to the bones and muscles to the tendons of the human body. Tensegrity is clearly nature's preferred building system. Only tensegrity can explain how every time you move your arm, your skin stretches, your extracellular matrix extends. That's the collagen network. Your cells distort, and the interconnected molecules that form the internal framework of the cells can feel the pull without any breakage or any discontinuity. 30 trillion cells in your body. This is going on all the time, right? Did you just have your mind blown again? I hope so. It blows my mind every time I read this. Now, many years later, Don Ingber is running the Weiss Institute in Boston, and he has a young intern working there. It's an amazing lab. It's like Disneyland for me. It just, like, it's just an amazing place. Every lab should be as cool and well coordinated and put together. I gush, but there's a reason. So anyway, let me talk about what's on your screen. So this researcher, Bo-ri, Seo, she's Korean. She figured out, she worked with the robotics department that's in the lab and the materials place that's in the lab, and she created a tiny little robot with a tiny little rubber tip that would go boom, 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 and it would give the same amount of pressure in the same area consistently, however long they wanted to do it. Now, what you see on the right is a muscle that has been infiltrated with neutrophils, which is a cell in your immune system, and they're good. But if they hang out too long, which is a thing that can happen, they wind up like putting their feet up on the couch, inviting their buddies over, and you get too many neutrophils, and your tissue doesn't heal properly because it's got too much going on in the immune system. So that's all the bright pink that you see in the blue is this overabundance of neutrophils in inflamed tissue. So what Bo did is she got this tiny little robot. By the way, that's a rat that has that inflammation. And she got a little robot to go boop, boop, boop. And then they took another picture, and you can see how fewer neutrophils are in that same area of tissue. So this general mechanical pressure, acupressure, acupuncture even maybe, helped clear the neutrophils out of the inflamed, damaged tissue. And there's Bo-ri. And that was her when I asked, I was interviewing her, and I said, "So, Bo-ri, are you telling me I'm going to be replaced by a robot?" And I'm starting to worry about that. But that's another lecture. So Don looked at this and he said, this is describing a new form of mechanotherapy that could be as potent as chemical or gene therapies, but simpler and much less invasive. So there's another picture you see there of the pre and post. On the left is the neutrophil invasion. On the right is post mechanical therapy, pressure, and the changes that happen there because we are designed to respond to mechanical pressure, mechanical forces in our body. And it has much more impact on us as you can think. So I hope your mind just got blown again. So this leads us to needle grasp, which is, I've been informed, is sometimes called obtaining chi. So there is that phenomenon that you acupuncturists know where you put the needle in and you almost feel like the body goes, oh, I want that. You get like this little pull that you're not doing. What's that about? Am I just imagining that? No, you're not. Because there's a wonderful researcher in our world called Helen Langevin who was very fascinated by this too. And she decided to use ultrasound to image what's going on in the needles when we're pulling them in and we're twisting them. Okay, so it's not just putting the needle in, but it's the twist, right? So you put it into a tiny twist and it's like, oh, there's that pull. What is that? Well, that's what this is. That's the picture of the collagen fibers wrapping like spaghetti or ramen around the acupuncture needle and pulling it down a little bit more, probably activating mechanotransduction. How could it not? How could it not? And this leads us to the idea not only does the fascia connect on the cellular level, it connects on the broader level. So what you're seeing on the left takes us back to the anatomy trains concept and the superficial backline that runs from the bottom of the foot up the muscle myofascial units of the calf, the hamstrings, the sacrotuberous ligament, and up the erector spinae to the gallia aponeurotica, the fascia of the head. And it pretty well mirrors the kidney meridian. If I'm not mistaken, that's the kidney meridian, right? Pardon me? Okay. Um, and Helen mapped out some of the yin, some of the meridians of the arms also correspond to some of the myofascial meridians in the arms. And according to my sources, Thomas Myers did not try to match this force transmission myofascial meridian system to the acupuncture meridians, but somebody took his work and did a compare contrast and said, you know what? More of these line up than don't. Some of them don't line up, but a lot of them do. And someone else who took it next level, because that's her job, is Helen Langevin. And she studied the arm and the shoulder. And she found out that more than 80% of the points in acupuncture in the arm correspond to over 50% of where the intersections are, where the fascial planes coincide with each other. So where the fascia from one part goes to the fascia of the other part. So can we say that all of the acupuncture points align along the meridians intersect with connective tissue plane crossover? No, if we're being good scientists, we can't. But can we extrapolate that if we're looking at these kind of numbers in one part of the body, we might find those kind of numbers in other parts of the body? I think we can extrapolate that, but no one has done the research yet. But it's research that is just out there waiting to be done. Maybe one of you listening right now is in a position where you could take this to the next step. There's the paper at the bottom. I suggest you look it up and check it out. Now, there is an electrical aspect to the fascia, which is going to take us into the nervous system. So another aspect of chi, if you will. So piezoelectricity, which is pressure-induced electricity. If you use a cigarette lighter and you pull the wheel, it's that spark that is generated between the flint and the metal. We have that in us too. So we're festooned with many, many, many sensory receptors throughout the body. We're going to see them in a moment. But we think that they work on a very small electrical charge, piezo pressure generated electricity. But the funny thing is, there's a helix to it that winds and unwinds when that signal is generated. And the piezoelectricity is also generated by the shearing stress, like I talked about earlier, in the sliding layers and what excites the fasciocytes to produce more hyaluronin. And it's that polarity, that negative and positive, just like on your batteries, one end and the other end, that allows these sensory receptors to fire and give our central nervous system information from the outside world. So This is what I like to call non-neuronal communication. We've done a mathematical estimate based on other areas of the body, and there are an estimated 250 million nerve endings throughout your fascia. And they are all these different kinds of nerve endings that you see at the bottom of your screen: muscle spindles, Golgis, Raffinis, Paccinis, and the type 4 free nerve endings, also called interstitial nerves. They're all the same thing. Your eyes are the next in line at 200 million nerve endings. Think about how small your eyes are and think about how tiny that has to be. But throughout your whole fascial system, your collagen matrix, you've got an estimated 250 million nerve endings. And again, we come back to the side we talked a lot about earlier because most of those type 4 free nerve endings, interstitial nerves, live in that sliding zone that you saw earlier in the lecture between one myofascial unit and another myofascial unit. And those nerves are responsible for our proprioception and our interoception. So if you're not familiar with proprioception, all you have to do is look at me right now. I've got my eyes closed and I'm going to touch my nose. I didn't need to see that to do it because I can feel it. I know where my body is in space and I can feel where my body is inside myself. And these sensory nerves are most abundant in these sliding zones. So when we develop those densifications I talked about earlier, those sensory nerves are not going to give accurate signals. In fact, if anything, they might give off a signal that feels like pain or at least discomfort. So they're a player in here. So whether we're using, like I do with manual therapy in my hands to increase the sliding in the zones, then the nerves kind of go like, oh, wait, we're having a different experience. I guess this isn't so bad. Or we're using needles or other means that create the same effect. This is part of how it works. This is how we reduce and get rid of chronic pain in many, many cases. Happens in my clinic all the time. I want to highlight one of my favorite places here and one of my favorite people in the universe. This is Carla Stecco. She is one of, if not our best researcher. I hate ranking things, but she spent 10 years working on one book to create a fascial atlas, a fascial medical atlas of the human body. She did all the sections, took all the pictures, wrote all the text. It's never going to be done again because no one else is ever going to do it. She did it. It doesn't need to be repeated. Um, and one of the things that she found in all of her published papers is that in the retinacula of the ankle, which you're seeing there on the right, and you're seeing kind of not so represented there on the dissection picture on the left, but it's that band of tissue that goes around the ankle. And it's also, we have one in the wrist as well. Well, the traditional anatomical view of that is that it holds the tendons in place. A little bit. But what's more interesting is that the fibers of the retinaculum go into the deepest part of the foot. It's a very intricate network. Remember the revolving thigh? Think about that like to a factor of 10. All those collagen fibers going from the retinacula into the network. And oh, in terms of the areas of the body that we've studied, there are 9 times as many sensory nerves in the retinacula as there are in any other part of the body that's been studied. Why do you think that would be? I'll give you a minute to think about it. So when you take a step, you've got to roll through your ankle joint, right? So when I roll through my ankle joint, I've got all these sensory nerves in my ankle going, hey, knee, hey, hip, hey, waist, hey, shoulder. Here's what's going on under my feet because you have to use your tensegrity to respond to every step I take. And again, this is why the slower and more mindful practices like Tai Chi, like yoga, can engender greater proprioception because we're paying attention not to just that we're moving, but to the quality of the movement. And this is an area that I work on all of my older patients because what I see way too much of it in my country. Um, um, one of the doctors I work with is like, I hate walkers. They just make people walk like elderly people because they don't really walk. They put their weight in their arms. And in a rehab situation, sometimes a walker is necessary. So I'm not saying they're wrong, but the problem is that if you don't get weaned off of them, you shuffle your feet, right? You don't flex and point your foot. Those proprioceptive nerve endings get no stimulation. So we actually make our senior population less stable the more we make them depend on outside devices. So the more I can get them to do safe flexion extension, maybe even use a med wrap or kinesio tape around their ankles to just stimulate those proprioceptive nerve endings through the retinacular cutis, the skin ligaments that Rochelle was showing you earlier, and engender more awareness to that area and restore that function, it's going to make everything else along their body feel stable. And it works. So let's talk a little bit more about the nervous system and tool use, because if you're an acupuncturist, well, that needle is a tool, is it not? Now, the philosopher Immanuel Kant said the hand is the visible part of the brain. So think about when you're walking with a cane, you can feel what's going on the ground, through the cane, in your hand. Have you thought about how amazing that is? Because what's in the cane that you can feel it on the ground? There's nothing. There's no nerves in the cane. It's not, what is that about? Well, there's this branch of physics called psychophysics in material sciences, and it's all about how different textures and different things feel and respond. So there's a field called haptics. So like how you feel when you press something on your phone is really important. That like, oh, I did something. Oh, I did something. Oh, I did something because I can feel it. Which is why haptics in elevators is usually really bad because you push the button and you know it's just not going to work. But there's lots of things that can change our perceptions about the surfaces that we touch. Things like roughness, how warm they get. And the sensory receptors that I've been talking about, those 5 little drawings that you saw a few slides ago, they are the most ancient in our development and in our development as a species on the planet. We were taught to feel, we were taught to sense before we were taught to hear, before we evolved to see. All of our other senses, touch came first. So I think they're, oh yeah, you're the old timer. No, we're the most exquisitely developed. And there was a experiment that was done where they created a they created a metal, they created a substance where they were able to replicate it 1 molecular layer thicker. Okay. They had and they worked it so that it would always have like the same texture, the same heat reaction, because hot, cold makes a difference to how the sensors in our fingers respond to the surfaces that we touch. So they put it on a dish like that, and there's 3 strips. 2 are the same. One is 1 molecular layer thicker than the other. And they gave it to, I forget how many hundreds of people, and they just asked them a simple question. Which one's different? 71% of the people got it right. That does not happen in science. Those kind of numbers are off the charts crazy. And it just shows you how just we are naturally imbued with that sensitivities. These were not acupuncturists or massage therapists or myofascial people, just normal people doing normal things. 71% could tell the difference in something 1 molecular layer thicker than the others. So when people say, you're not feeling anything under your hand, you're making that up. I beg to differ. Um, these results are considered way above chance. Um, there is a pre-neuronal stage of mechanical information processing. So think about spiders, think about mice, rats, those little whiskers in the front of the mice. They are sensing the environment ahead of the creature. And they're sending that non-neuronal processing to the brain to tell them what's in the environment where they can't quite see yet. Or in the spiders, what's going on around the web. And what we've learned from this experiment and other experiments, and I don't think I have that slide in this deck, but they did one with a rod and a tool, is that tools are treated as sensory extensions of the body. What is it about our the sensitivity of these when I put that cane on the ground, I can feel the ground underneath me. It's this miraculous, mysterious thing about our body that can do that. And here's how they did that. They used that rod and they had different, you can't see the rod. You can see a picture of it if you look at that from the top down. And then there's somebody on the other side of that wall touching the rod in different places. And they had to say where they felt it along the rod. 90% accuracy. It's crazy, right? But I'm going to quote Darren, who runs the lab. Love Darren. It's not just the mechanoreceptors in the skin, but the receptors in the ligaments, the knuckles, the wrist, the elbow, the shoulder that could be enabling humans to sense minute differences using touch. And I really want to have a conversation with Darren about fascia someday. I hope I get to do that. But I hope you can see how this fits together and also with the concepts of tensegrity, all the way down to the cell, all the way up to the skin. Now, here's where your patients and your clients come in. Here's another off the charts crazy experiment. So this was a PT named Lorimer Mosley, and I won't get into the weeds of the details of how they did the experiment, but basically they had two groups of people with the same condition. They each got the same therapy. One group was allowed to read a book, listen to music, check out, whatever, get your therapy, come back. And it was chronic chronic limb pain, CRP. It's really tough stuff sometimes, chronic repetitive pain syndrome. The other group had to pay attention. They had to say where they felt the intervention. They had to talk, about the quality of the intervention. They had to give feedback to the therapist about what was going on. Everybody in the group that gave feedback got better results than those who were not paying attention to their therapy. 100%. This does not happen in science. What does this mean? What is this telling us? How should this change how we think about our therapies and how we employ them? But wait, there's more. Effective continuous touch on brain functional connectivity is modified by the operator's tactile attention. So in another experiment, totally different people, the use of functional MRI on the brain. And one group, the operator, the person touching, was touching the person on their shoulder, and they had headphones on that were playing a series of beeps. And they're supposed to pay attention to the beeps and say how many beeps they've heard. The other group didn't have headphones. They had their hand on the same side of the body of the people they were touching, just holding it there. Feel it. Pay attention to the contours. Pay attention to the heat differences, but focus on where you're touching and what you feel. That's all. Nothing therapeutic, just touch. And the MRI is scanning the brain of the patient, not the person doing the touching. And what they found was that when you pay attention to what you're doing and what you're touching, as opposed to checking out, it changes the way the brain processes the information. I don't understand how this works. Could it be that we have seen evidence for attention and intention? That what I'm paying attention to when I'm doing my therapeutic treatment makes a difference on the person receiving the treatment and gets a better result. The results show that if particular cognitive status of the operator is sustained over time, it elicits significant effects in the subject's functional connectivity between areas processing interoception and the attentional value of touch. You're not going to get that with a massage robot, okay? I'm just going to say it. You're not going to get that with a massage robot. It may have AI, but it's not going to give you attention. And this suggests that touch focused on myofascial movement would more accurately trigger the afferent fiber receptors that light up those cell receptors via piezoelectricity, cascading a bottom-up effect of neurobiological events. A lot of mind-body medicine is about, let's use the mind to change the body. Well, what if we use the body to change the mind? And it ends with distinct involvement of specific areas in networks in the brain, all through the quality of attentive, focused touch, attentive, focused needles. And the founder of osteopathy used to say that the fascia, that's plural, fasciae, the fascia are the branch offices of the brain itself. And he's an old timer from 1899. How did he figure that out? Nobody's really sure. But the evidence is mounting that he was not wrong. He was much closer to right than he was wrong. Now, at the University of Pittsburgh, we did a mind-body program for older adults with chronic low back pain. I would like to tell you I was involved with it. My department was involved with it, but I was not consulted. And they did a preliminary pilot study, but it was intriguing results, but the numbers were too low. So they replicated it, and they had like a 70-80% rate of completion among about 100 participants, as I recall. But the whole point was used to use mindfulness-based meditation to just sit with what was going on. And they found that 35% that the people who participated in the mindfulness study on low back pain had a change in their perception of the low back pain. Now, they measured it for mechanical changes, so they didn't move better, but the quality with which they experienced the daily low back changed and got better. And I love that. And I've heard supposedly that people, monks who meditate, don't have low back pain, but that may be anecdotal. I don't really have good data on that. But here's the other thing. I don't have the slide for it, but there's a study done by Robert Schleit where they put different biochemical substances on fascia to see what it would do. And they were looking for things that would make it contract and get tight. But buried in that paper is the fact that a molecular precursor, so it's kind of like, well, we're building the thing right now, but we're going to make it, to nitric oxide, caused the fascial tissue to relax. And that to me is the best part of that paper that everybody misses. And what happens when you meditate? You create more nitric oxide. We did a study on meditation and low back pain, and it changed. Could it be the nitric oxide? I think this is worthy of more investigation. So where is this connection between the fascia in the brain, the body and the mind and the brain? And it's all one and the same anyway, if you've been following the metaphor of the land and the water. But this is the anatomical location of the myodural bridge. So what you're seeing there is the spinal column. You're seeing on the A, the suboccipitals, and the B portion is the myodural bridge, which is blown up on the right. And you're seeing a histogram there with the muscle tissue to the right of the screen. And then what you're seeing in that area that's shaded in the circle C, that's where the mechanoreceptors in the fascia from the muscle are going into the brainstem. So there is a sensory component in the brainstem, in this myodural bridge, that I'm not saying is the sole generator of this, but it's got to be a player in this mind-body connection. And partly how the body communicates through itself into the brain from the outside world into the inside world. And there's the slide about the nitric oxide in the wrong place. So now you have that. You can take a screenshot. You can look up the paper. Whew, I'm not as old as I think. Now, last but not least, the great thing is that fascia regenerates. That's why you get the results you do. That's why I get the results I do. So this is a picture. This is a ultrasound image of a healthy collagen network. And then it was in the arm, and they put the arm in a sling and they immobilized it for 3 weeks. So remember how I told you fascia responds to supply and demand, and all the cells, you got the cells that make the hyaluronin, you got the cells that build the collagen, and they need that regular motion. Well, I didn't give it regular motion for 3 weeks, and that's what it turned into when they took a picture of the same area. Now, if we anthropomorphize on a cellular level, that just don't look right. It just does not look good. Without that regular stimulation, the collagen grew like crazy, which made things stiffer, crankier, and harder to move. But fortunately, fascia regenerates. And I'm going to conclude this portion of the lecture uh, with another one of my favorite studies. So what you're looking at here is a living active cell culture. A lot of times cell cultures are not, they're really in a lively state, but this group is. And it's on a flexible substrate. It's on a surface where they can mechanically manipulate um, the cells. So they did that for 8 hours. So I don't know about you. I see a lot of repetitive motion injuries in my clinic, people doing the same thing the same way. And, whether it's playing pickleball, which is really big right now in my neck of the woods, or they have a job that's very mechanically repetitive, but then they go home and they just Netflix and chill and don't move very much. And they develop these restrictions from repetitive motion. Well, anyway, they gave the cells repetitive motion, and here's what happened to the cells. They lost hydration. The intracellular connections were broken. 30% of the cells died off. That's that same group of cells after 8 hours of repetitive motion. And then because this was a flexible substrate, they were able to reformat it. So they were adding pressure, like you saw on the slides with Boeri in the immune system. They were also able to put some stretch on it, like we saw with the tensegrity of the cells, but they also were able to do some shear. They were able to bring some glide in, okay, like we saw with the fasciocytes. And they did it for 60 seconds. They just picked the number at random. Boom. Look at the difference. So from this, they were able to conclude some of the cell-to-cell communication was restored. It got juicier. It got more rehydrated. Um, so they kind of concluded from this, and it's really needs to be replicated, but it hasn't been, is that 60 seconds of myofascial release has the potential to undo 8 hours of repetitive motion strain. It's not rocket science anymore. And the last picture, they took us, that's a cell culture that they didn't give 8 hours of repetitive motion strain to. They just did myofascial release on it. And I don't know, they look a little plumper and happier to me. But they just want to say, okay, like what if we just don't just do it without the strain? And you can see that that obviously had an effect on the morphology, on the shape of the living cell culture. But I think these pictures speak for themselves. So is it mind? Is it body? Is it fluid? Is it fiber? It's all of it. It's all in how we choose to work with it, manipulate it, and see the results that our patients and our clients and the people that we serve get in order to get them the best possible results using all of the tools at our disposal. I'm now going to turn things over to the wonderful Rochelle Clausen, who will take you on a deep dive into fascia as it's never been seen before. And I do mean that. Rochelle. Whatever you want to do. I'm good. I'm good. Just we'll flip it back to me for the very
Yeah, great. Thank you so much. Love this topic. Love those images. It's so amazing to just study this detail about what the human body is made of and how we're put together. I've already been introduced, so I will move past this slide. But what I want to talk to you about a little bit today is the Fascial Net Plastination Project. This project was a collaboration with Body Worlds. Body Worlds, you may be familiar with. They have done some amazing work showing the human anatomy to a public audience by finding a new preservation method. Plastination is a preservation method that allows you to see true human tissue outside of the lab in a way that is permanent. It halts decay. It has no smell. It has solidity that allows us to see things that we never have seen before, and even more so with the genius of the positioning of Body Worlds to be able to show what very lifelike um, cadavers in postures and positions that you and I are in every day that really helps us translate what we find in our anatomy books to our own moving, living, breathing anatomy of every day. Gunther von Hagens is the man who discovered and invented and continues to invent new methods of plastination and preservation for different ways to see. And this didn't start yesterday. It was actually in the early 1970s when he first developed this method, but it took until 1995 that they figured out how to apply it to whole bodies, which is when the first plastinated specimens were publicly displayed at the National Science Museum in Tokyo. And Dr. Angelina Wally was a visionary that had the vision of bringing this to the public and not just to the medical communities for the purpose of people understanding their bodies for health. Her idea was that if we could understand our bodies, we would take care of them better. But there was something that was always missing from the Body Worlds exhibits. Sorry, let me just this fact. 450,000 people, it was so popular, came to see this exhibit in only 4 months. But fascia was mostly missing from every specimen, not in its entirety, but largely, which is where the fascial net plastination project had its beginning. You may have heard Dr. Robert Schleip's name mentioned already. He's the director of the Fascia Research Group. He was the co-founder of the Fascia Research Society, and he continues to be the director of the European Rolfing Association. And he was the initiator and scientific advisor for the Plastination Project. This is a little timeline of when I met him was back in January of 2014, when he first brought fascial fitness to the US and to California. And little did I know that our connections would continue for many years. So his initial reaching out to Body Worlds, and quite a few people in the worlds of fascia research did reach out to say, can we create a fascial-focused plastinet? And Body Worlds had up to then said no, partly because it was too complicated. It is a very complex and pervasive system. Body Worlds is also Von Hagen's plastination. Body Worlds is the public-facing exhibits, whereas Von Hagen's plastination are the medical models that are used in education for surgeons in medical schools. So these three entities then came together and they agreed. Somehow it was the right timing and the right energy was there for the Fascial Net Plastination Project to have its start. Carla Stecco, whose book you can see here, The Functional Atlas of the Human Fascial System, was also played a pivotal role in this as one of the primary initial advisors. She is a fascia researcher, orthopedic surgeon, professor of human anatomy and movement sciences, and the scientific advisor for the Fascial Net Plastination Project. And she's in Padua University in Italy. I also met Carla very briefly in September in Washington, D.C. of 2015, and also just delighted of how much we have been able to work together on this project as we continue to expand people's understanding of the fascial system. Gary Carter and I had met just months before this project had its inception in Ulm, Germany in 2017. And you can follow the timeline all the way till just this year, where we taught together in England and studied together with Carlo Stecco in Italy. And he was a key player because he has the artistic capacity, ability, and design background that he was a huge part of the final plastinet that we'll show you in just a moment. The journey, though, is part of the story. So this is actually where the laboratories are located in Guben, Germany, at a building called the Plastinarium. It's both a Body Worlds exhibit as well as the laboratories where plastination happens for all of the Von Hagen's plastination specimens, as well as all of the Body Worlds exhibit specimens. And it became our second home through the course of the years that followed as we started this project. This was a hugely collaborative project. The Fascial Research Society put a call out to all of its members for anyone that wanted to apply to be a part of the creation of these. This idea was to have a full body, if not more, full body plastinets to show the human fascial system. And you can see Carla Stecco and Robert Schleip there, as well as many, many other educators in our field that gathered together for 5 days to get started on this project in 2018. Some of our inspiration, as was already shown earlier, came from the work of Bergerie. Bergerie's Human Atlas of Anatomy and Surgery was written in 1843, and remarkably, his representation of the fascial system exceeds a lot of what you'll find in your basic anatomy books these days, highlighting the interconnectedness of not just the deep fascia, but even in this picture, you can see the compartments of the deeper tendinous structures, but even the more delicate structures of the epimysium of the muscles. So we started by replicating some of his work and seeing if we could. And it was actually very challenging as we realized how integrated everything was and how fragile actually the fascial planes could become if you teased muscle away because they were so integrated, the strength would be lost. And so we'd have collapsing compartments. And we thought, wow, that's easier if you draw it because you can draw them to have more stability than they do in real life. But this beautiful dissection was done by Tracy Meller as we worked through this project with these initial specimens. This one was done by Jahan Adem, a very skilled dissector, and taking it a step further, not only showed the compartments of the fascial enveloping bags of the muscles and of the entire limb, in this case of the thigh, but also reflecting layer by layer. You can see on the right side of your screen, just reflecting skin, just reflecting superficial fascia, and then you can see the deep fascia. You also may notice the red that is in the plastic, or sorry, it's actually just a formaldehyde fixed preservation tissue that's on the right. At the plastinarium, oftentimes they will inject the arterial system with red plastic in order to be able to see where all of the vessels live. So that shows up a lot. So as we were doing these initial dissections, those were of the deep fascia, and now we have also the superficial fascia. And at one point, we turned the lights off and backlit this superficial fascia. The one you're seeing here has actually partially gone through the plastinating process. But at any stage, this otherwise somewhat white, maybe yellow tissue, when you backlight, has this radiance. There's no blood in this tissue anymore. So all of that warmth and tone is coming somehow the way that the superficial fascia is refracting light, which gave us a bit of an inspiration on the naming of our first exhibit. As we were taking pictures, you can see Stefan Westerback there and me holding the light for him. We named the first exhibit that we did Fascia in a New Light because we really thought that that captured so much of what we were trying to see, both philosophically, theoretically, but even physically, seeing fascia with light to help us understand the depth, the dimension, the three-dimensionality of it, and its pervasiveness through the body. So this first exhibit was done after the initial plastinates were created, which was not a full body, but just simple specimens. This was our team as we regathered in Berlin about 6 months later when those first specimens were completed. We were at the Fascia Research Congress in 2018, which was held at the Urania in Berlin. And these are the 10 specimens that were completed. There was a lot of testing to see if the process would work. Like I had said, that Plastinarium and Body Worlds were not really excited about the project initially because they weren't sure if it would be successful and they didn't want to attempt something that was going to fail. But you have to try to see. And so they were very pleased, as were the Fascia Research Society members, to see how beautifully these plastinates turned out. I'll just quickly look across the top row, starting on the left. Those are superficial fascia of the abdomen, followed by a superficial fascia strip that was unwound and laid flat, which was initially wrapped around the thigh. And then a complete dissection of the superficial fascia of the thigh at the knee area. You can see back under, or backlit, but there's actually a light inside of the tube-shaped structure. And then the elbow. And then one we'll look at a little bit more, the entire enveloping fascia of the thigh, the fascia lata, with the gluteus maximus, as well as the tensor fascia lata still embedded. And then we moved to visceral fascia and this incredible dissection of the pericardium. There is no heart in that heart, just the outer fascial wrapping connected to the tendon of the diaphragm with part of the diaphragm muscle still connected. Is the one on the second row on the left. And then cross sections of the thigh and of the leg showing us how much fascia there is in our body, so much of this collagen network. Looking a little bit more closely at the superficial fascia, earlier in the presentation, I was showing you pictures from the lab. So that picture on the far left is an unpreserved tissue from a cadaver that has been dissected. And then you can see the plastinated one from the same region with a close-up. And when we look close up at the backlit plastinated fascia, remarkably, you still can see those fat lobules encased in their honeycomb architecture of the collagen network. The lines that look like trees reaching through are, as you would imagine, the vascular network, which much of it is in the superficial fascia. There's miles of blood vessels in your superficial fascia. Looking again at the specimen I mentioned before, if you remember earlier in the talk, we were looking at this silvery collagen network that envelops the entire thigh, giving strength and stability and force transmitting capacity. When we dissected it, we decided to leave in the muscle that is truly embedded in this layer. You've probably heard of the IT band is often referenced as being a tendon of the gluteus maximus. However, in this image, you can see how there is no start or stop. The IT band is not so obvious. Looking up close, you can maybe determine where the fibers start to get a little bit less thick, and that may be where the dissector would then cut and separate those tissues and say, this is the IT band, but it is not in any way a separate structure. Rather, it is a thickening and a reinforcing of the fascia lata. The cross sections we actually had in this three stacked on top of each other are from the leg below the knee. And when you look down through the holes in the openings, now that all the muscle has been removed, you could almost see that the way that the muscles sort of spiraled and twisted as they would go down towards the ankle, just giving another view of three-dimensional anatomy of the fascial system. The viscera, once again, so this plastinet on the left is actually from the plastinarium, and it's one of their beautiful dissections showing the open chest cavity with the pericardium curled back like the leaf of a book peeling away to show the heart beneath. Whereas the image on the right was created by the plastination project, and we just removed the organ altogether, only leaving the pericardium sac behind. The exhibit was visited not only by the Fascia Research Society, but it was actually a dual is an event where there was an osteopathic convention that happened after that we were able to also have this exhibit on display for. And I believe over 2,000 people were able to see these plastinets. I can't remember the exact number, but that's what sticks in my mind. Does that sound right? Do you remember? Somewhere around that. And it was a very busy place because this was a view of fascia that very few people have ever seen. This is the first time this has ever been done, as far as we know, to this extent. So many conversations and debates and discussions as talking about and knowing about fascia, almost in some ways more on the microscopic level, being able to see it on the large level was phenomenal. Which brings us to, of course, the goal of the whole project, which was to create a whole body plastinet. This plastinet was given the name Freya, initially after the goddess of love, of the Norse god of love, but we mixed with the spelling of it in order to create an acronym that held meaning for teaching purposes, calling her Freya, Fascia Revealed, Educating Interconnected Anatomy. We went back to the labs and we had, over the course of 6 months, we had 5 groups of dissectors that came working ever so carefully to make sure that we didn't cut away anything we mean to leave. When you're working on individual specimens, it's quite easy to make mistakes and not worry about it. But when you have a whole form, everything stays and everything matters. So we started off by creating some practice pieces to get an idea of design. We had to decide, how can you show fascia, which is quite the tissue of connection, through the act of dissection, which is separation. And this really puzzled us for quite a while. So the design process was complex, long, and got revised many, many times. But initially, we just started to see, how can we show these different compartments? So this piece you'll see again at the end of the presentation, which was plastinated to show the different depths of fascia, starting with the just beneath the skin, and then having this cross section to be able to create the different levels as the muscles emerge within their compartmental sleeves. And the periosteum is really beautiful on this picture. So if you look and see the femur right in the middle of the picture in the center, you'll see all those blood vessels that are in the very thin fascial tissue that surrounds the bone. So this is the team that got to work. We had a great panel of advisors, including Dr. Vladimir Chereminsky, who is the director of anatomy at the Plastinarium, Gil Headley, a well-loved and very long time known fascial dissector, as well as Tom Myers. You're probably familiar with his work. We've been talking about it today. John Sharkey, working with his school in England, and Robert Schleip, sorry, he's in Ireland. He's in Ireland. Sorry, John. And then Dr. Robert Schleif, Carla Stecco, also consulted with Jaap van der Waal, and of course, Dr. Gunther van Hagens and Angelina Wally. And so this team continued to gather throughout the process as we designed this new full body plastinet. Several of us served as directors to make sure that all the parts kept moving smoothly. And this was the dissection team that came together in different groups. There were only 3 or 4 at a time as we worked on Freya over the course of that 9 months of dissecting. Phenomenal group of people. We had such a good time working hard on something that had never been done before. We were very inspired to be a part of this. And the models that were made, as you can see, there's Gary and I sitting on the floors. We did many, many nights with all the anatomy books spread around and all of his drawings spread around, and even drawing on his own body to try to express what we were thinking. He made models out of paper, reflecting the layers, seeing how we could not take the fascia completely off or take the muscles completely out, not of a whole body. It's not possible. It's too integrated. So we realized we needed to just create windows, ways to show tissue relationships, not just fascia on its own. Fascia is not on its own. It's the thing that connects all of the things. But to demonstrate the different types of fascia with clarity, we came up with many, many different organizations to show that. I'll just take a moment to say here, as I'm about to show you the final product, is that fascia is not just everything everywhere. Fascia is not just a net or a spider web that connects the body. It has many very specific organizations with specific jobs to do. And we wanted to be able to show that in Freya with as much clarity as possible. And so the final result was stunning. She exceeded our expectations, both of the plastinarium as well as those who worked on her and did the efforts. A team that you didn't see pictures of was the plastinarium team that not only did the plastinating process, which took another 6 months, but also the final positioning, making sure that every single part of her was in place and well supported so that she would last and through the test of time and educate many, many people from all over the world who come to see her. I want to just take a moment also to thank Freya and whoever she was. We don't know her actual name, but her donation was intentional for this purpose. Her donation was specific to this, not to the project of itself, but to Body Worlds to be used in a way that would serve the living. And those of us that through our work and through our hands-on therapies and through whether it be Chinese medicine or manual therapy or physical therapy, that we're serving by learning from those that were generous enough to share their remains so that we could teach from their forms. Stefan Westerback was the photographer for our group. Both of us were, but he did many trips to take pictures of the process along the way. And I just thought the way he said this was so eloquently stated. In each quadrant, there slowly appeared windows. Every window opening a completely new story of Freya, full of anatomical details and fascinating structures. And if you look into a window from a new angle, then another story awaits. So we created a book that was, it's not available for sale, unfortunately, but we created this book for all of the attendees of her unveiling, which was in Montreal at the Fascia Research Society's Congress. And we spent a lot of time going through labeling all of the different aspects of her fascial system to help identify these tissues because this kind of image is really hard to find anywhere else in any other form. So let's look just a little bit more closely at some of the fascial windows that we created on Freya. Starting with her cranial fascia, you can see right above her eyebrows in the center of her skull, the skin still remains. And that's starting at the surface, at the dermis, the beginning of the fascial system. And then going deep to that, the superficial fascia was revealed, followed by the gallea aponeurotica, and then the periosteum that all lies superficial to the skull bones. Deep to the skull, you can see a big flap that was created, and that window, of course, is into the very famous dura mater, a very strong fascial system that's a part of the central nervous system. As that's reflected back, the arachnoid and pia mater are shown on the surface of the brain. And with a close-up, we would even be able to see the vascularity that is there as well. There's many, many things to describe on Freya, so I'm just going to hit some of the highlights. We really wanted to convey this concept of from skin to depth. So there remains a spiraling strip of skin that goes down from her shoulder all the way down her leg and spirals towards her foot so that you can see relationship again is more important than just seeing tissues on their own. So number one is numbered as the skin and then down to the superficial fascia. This is on the right gluteal side of her pelvis. And then you can see the muscle of the gluteus maximus and the deep fascia that is still covering it, followed by the thoracolumbar fascia, which of course the gluteus maximus feeds into. Um, Showing these distinctions as well as how they're connected to give us a model that reflects the reality of the living form was the goal. This is from the posterior view of the right shoulder. You can see the trapezius is colored red on the top, and then very quickly the red disappears, and we're just so used to seeing the muscle body that it's so unusual to see all of this white stuff. Well, that's the collagen network. And it's important to say at this point also that the process of plastination dissolves all of the lipids. There is no adipose remaining in any of these images at all. What you're seeing is the other part of the adipose tissue. You're seeing the collagen network, and it's a lot. It's more than you might think. As we look at the other pictures from the fresh tissue, you think, oh, that's all fat. But once all that fat is dissolved, look at how much remains. It's so significant. The deep fascia of the trapezius is numbered as number 2, and then we created another little flap to show the superficial adipose tissue, the superficial fascia membrane, sorry, and then the superficial fascia adipose tissue is reflected back as a curl, and that curl cascaded down her back and down into around to the front as well. And then the skin ligaments are actually visible on this to be able to see how the retinacula, cutis, superficialis are connected to the skin. So if you can see that on number 5. And then number 6 fell off there, but that would be actually the skin itself. So then Joel Talsma was one of the anatomists on our team that worked with us, and he's the assistant professor of anatomy at the University of England in Portland, Maine. And he said, I have hope that Freya will teach and inspire a multitude of people to not only learn the anatomy, but to also have an appreciation for what is creating the framework of the human body. So not so much the separate parts, but what makes them a whole. And I just remembered Joel's moved since then. I think he's in Boston now. I'll have to find out if that's true. Is that right? I think that's right. He definitely has moved since this project. Okay, so let's look at this other concept of all around. I wrote this as the idea was that there was like pages of the book. There's so many pages of these flaps of fascia or distinctions of the fascia. So the fluttering pages of the external and internal obliques and the transverse abdominis converge through their flat tendons to create the multi-layered rectus sheath in the front, as well as the anterior aspect of the thoracolumbar fascia in the back. There's a typo, we'll fix that later. So here you can see as we're going down into the depths, and this is something that is quite easily seen again in the dissection lab, but a lot of people don't study in the lab or don't have the privilege or the opportunity to do so. And so if the drawings are the only thing we have to go off of, and the drawings aren't showing us these tissue relationships, it's easy to have gaps in our mind as to how these are related to each other. Looking at the posterior view of the torso, you can see quite a few flaps curled back to see windows into where the muscles are, kind of almost to keep you oriented to where things are, because there's so much white in this form, being that the collagen fibers always show up as a glistening silver or translucent or white color. So on the surface of thoracolumbar fascia, you can easily see those collagen fibers, and you can tell slightly better on some of the other images I showed you how they form in a oblique axis, which flow in continuity with the latissimus dorsi and the contralateral gluteus maximus, the forces that transmit in a diagonal shape from one arm to the opposite leg every time that we take a step. Both of these muscles have fibers that insert directly into the thoracolumbar fascia, creating a line of force transmission that is continuous and without interruption, even though the muscles are considered separate. You start to see how they're connected. Even more so, we go up and down the full length of the body and we see that superficial backline, like we were talking again, is proposed by the anatomy trains concept. Freya shows these myofascial interconnections head to toe. And if we start at the bottom, we start with the left plantar fascia, go through the Achilles tendon, up through the calf muscles to the hamstring attachment, which is in continuity with the sacrotuberous ligament, then through the deep layer of the thoracolumbar fascia to the erector spinae, up and over the head through the Galleria aponeurotica and ending with the frontalis at the eyebrows. So this is just the lower part of it, but we've reflected that crural fascia back so that you can see within that compartment where the gastroc and the soleus live, but see the continuities and the connections. This picture also references the previous dissection that was done that had the fascia lata, and then how we recreated that same design in Freya. So we actually, this is part of the genius of Gary Carter, is he said, you know, fascia is all about continuity. He wanted continuity to go through the exhibits. Those first pieces that we did, we didn't actually expect to have an exhibit of. We didn't realize that they had so much value, not just as test pieces to see if we could do what we were trying to achieve, but created this incredible educational exhibit. So he took those pieces then, and we wanted to see if we could show that again on the full body to give a continuity of concept throughout the story of the plastination project. And then this picture shows a little bit further back, so you can see that continuance from the plantar fascia all the way up, showing you on models of others where that sacral tuberous ligament is. The idea of ligaments being separate from tendons, being separate from muscles, it's easy to get trapped into the idea of parts, but the parts are only created when we take them apart. The human body is not a machine that was assembled. You can't just, unfortunately, as much as we would like to, you can't trade in a broken part for a new one and have it be exactly the same as the original. As embryos, we grow ourselves. So the continuity and connectedness throughout the human body is thorough and profound. And so this helps us to see those connections again, maybe in a different way or enhancing our perspectives. This is the dissection that I did specifically on Freya, and this is of her forearm. And you can see the ribbons of tendon as they head towards the wrist as we've opened up the compartment of the extensor group on the back of her forearm. And you may be familiar with the different organization of muscle fibers. There's quite a few pennate muscles in the forearm and a lot of the below the knee and below the ankle. This allows them to have a great level of force with these long tendons with lots of fibrous connections, not just to the bones, and not just to the tendons, but also to the enveloping fascia, as is demonstrated in this dissection. We see another view as how it's shown a little bit different lighting. You can really see, especially in that center picture on the dissection that's opened on the far left, how the fibers of that muscle are rooting into the fascial bag of the antebrachial fascia. And then it was time to share Freya with the entire group of the Fascia Research Congress. Now, after the pandemic was opening us up enough to be able to meet, we originally were scheduled for 2021. It got pushed to 2022, and Freya got shown on display for everyone that was there. It was quite a thing to have to carry her through the elevator and put her on display. It was a very terrifying process as we were very concerned as she was a large shape and trying to make her safely arrive to her destination. And then on the far right, you can see the moment before we did the unveiling to the group in Montreal. During the time in Montreal after our initial unveiling, many groups of people came back many times looking with deep curiosity to try to put together all of their concepts and understandings of fascia into this unified, beautiful representation through the plastinet that we call Freya. You can see Freya for yourself. She's on permanent exhibit in Berlin at the Body Worlds exhibit that is right at the base of the TV tower, which is a very famous landmark in Berlin that you can see from just about anywhere in the city. If you happen to get there, I highly recommend having lunch in the tower so you can see. And then afterwards, you go down and see Freya in this exhibit space there. The exhibit for Freya is not only Freya, but they've dedicated a whole section of the museum there for the study of fascia. So quite a few plastinets exist in that room, including the one you saw earlier, which was one of the very first pieces that we did as we were preparing to create Freya, and some of the original drawings you can see there as well. Johannes Freiberg is from Sao Paulo, Brazil, and he's been a huge part of the Plastination project. He has such a poetic mind too. He would say some of the most beautiful things. So I felt it was appropriate to share this quote. He said, "It is no longer possible to be the same after this work. My view on fascia has totally changed me." So after the plastinates that we had in the first exhibit, Fascia in a New Light, and then after Freya and the exhibit that's in the Berlin Body Worlds, there was a request to have another collection of plastinates created that we could potentially share at other conferences and around the world. They currently live in Padua University, but let me briefly show you the team who created this last set of, or I should say, the most recent set. We hope there will continue to be more plastinates, not just by our team, but by the Von Hagen's plastination as more interest in understanding and research of fascia comes to light. So this is one of the pieces. You may recognize it as looking similar. We're taking our skills and kind of sharpening them and being able to show even more fine detail. I'll draw your attention to the far bottom left corner of this image, and this would be in the orientation of it. This would be of the quadriceps of the anterior compartment. Coming off of the femur there, but you can see on the outer edge, that's the deep fascia. But as it's actually being separated away, you can see they were actually able to preserve the loose connective tissue, which really surprised us. So this thing that's mostly water, and without going into all the detail of the process of plastination, basically boils down to getting rid of all the water and replacing it with plastic. So if the water is gone, one would imagine that those glycosaminoglycans and the fiber delicate network would just collapse on itself, but they were able to actually stretch it post-plastination to still show those fibrous connections that give these looser and more gliding planes. Some of the labels, the yellow labels are the labels that are about fascia. The white labels are the ones that we're most used to seeing, which would be naming the things as opposed to meaning the muscles, as opposed to the things around the things, which would be the fascial network. So this collection, like I mentioned, is in Italy. It's at Padua University under the very good curation and often tours being given by Carla Stecco herself. This is the university where she does her research. And this is me in one of the anatomical theater where Vesalius is taught, which just boggled my mind to be such a deep part of history and be able to still see it today. That's Gary Carter and I. We were there earlier this year in the spring, and we were able to share these plastinates with the group that was there for Carla Stecco's winter school with her research team. So there's been a total of these three collections of fascia that now exist into the world and now exist hopefully in your minds too, that I always suggest to my students that when you are trying to work on your patients and your clients, that you're often going off of the maps that are in your mind. But if those maps have holes or missing components from it, then you're not working with a complete picture. And how can your palpation or touch be complete if you haven't seen all of the things that you're touching? So we really hope that by having a little more information about fascia in a new light, Freya, and the FMPP collection, that this knowledge will expand rapidly and that people will start to have a more complete sense of the holism of the body as they work with their clients. Adrienne Woolley was one of our dissectors as well, and she also said many things that touched me as we worked together. But she said, for those of us who do manual medicine now, have a better understanding of what it truly is we are experiencing when we place our hands on our patients. But those who will gain the most from this profound knowledge will be our patients. And that is the remarkable gift gleaned from this FNPP adventure. If you'd like to learn more about the FMPP, please follow this link to our link tree where we have links to articles, videos, the actual unveiling of Freya that was done live streaming from Berlin during COVID, where we weren't able to have the Congress in 2021. Links to all of it is located there. So please enjoy and spread the word. If you'd like to learn more about me and my work in the dissection lab or with anatomy scapes, you can find my link tree also at linktree/Rochelle Clausen. Thank you so much, and back to David.
Thank you, Rochelle. And If you'd like to learn more about me, you can go to my website, which is my name, davidlesondak.com, just like you see there, or you can use the QR code there on the screen, which will actually go right into your contacts. And that has my email address, links to my books, links to my podcast, Body Talk. And yes, there's a lot on the Body Talk about fascia, but it's called Body Talk. So I enjoy having conversations with people who have work in different parts of the body and learn different things. So it's one of my funnest things to do. And actually, Rochelle was in my most recent podcast. She's been a pretty regular guest. She's a friend of the show, as we say in the podcast biz. And anyway, if you enjoy good conversations with interesting and smart people, I highly recommend you check it out. It's one of the most joyful things I do. I just want to leave you with one last thing. So I hope you've enjoyed all this. But so one of my early teachers used to put something like this up on the board, and he would say that 50% in the blue, that's everything that you know. Now that 25% is everything that you know that you don't know. Um, Actually, let me take that back. Let me flip that. Sorry, I got it wrong. Let's go on the left. So that 25% at the top in the orange is everything that you know that you know. The 25% at the bottom in the green is everything that you know that you don't know. That's a lot. But that other 50% over there, that's everything that you don't know that you don't know. And so his point was always fill in that 25%, make it 30%, make it 40%, because there's still going to be all those 50% that you don't know that you don't know. But he was wrong. It's worse than that, kids. So look at this one. So the orange, okay, remember I said that 25% in the orange was everything that you knew that you knew? It's worse than that. As far as we can calculate in astrophysics, I'm not an astrophysics, I'm just an astrophysics fan. All the atoms in the universe are about 5% of the known universe. So everything that we know is like 5%. And then we have dark matter. Now, it's called dark because it's opaque. We don't know what it is. So, like, oh, dark matter, it must be evil. No. Or it's like the mirror universe. No. Dark matter just means 27% of the universe is dark matter. It's matter, but we don't know what kind because we can't measure it, see it, observe it. And the dark energy, which is the energy we don't understand, is 68%. So, of the entire universe, all that we know is 5%. But doesn't that just tell you how much there is to still learn? How much there is? As Carl Sagan used to say, right now, somewhere, something amazing is waiting to be known. And we all can be a part of that. And I'll leave you with one last quote from another one of my favorite scientists who said, the important thing is not to stop questioning. Curiosity has its own reason for existence. One cannot help but be in awe when he contemplates the mysteries of eternity, of life, of the marvelous structure of reality. It is enough if one merely tries to comprehend a little of this mystery each day. Rochelle and I hope that we have helped you comprehend a little more of the mystery of our own body, this inner universe that we live in. And this quote comes from Uncle Albert Einstein. Thank you so much for your time and your attention. And I hope to see you one day in person. No, you can talk.